So this problem, integral e to the 6x over e to the 3x plus 1. And this is similar to the quiz question, but not exactly the same. We're going to let u equal e to the 3x plus 1. And our du is going to be 3e to the 3x dx. And then I would probably, so there's a couple ways of going about this. My preferred way is to do the following. I want to see, well, I can say I've got 1/3 du equals e to the 3x dx. And then I can see that I can break apart e to the 6x as e to the 3x times e to the 3x over e to the 3x plus 1 dx. And then what you can do is you can say, okay, well, there's my 1/3 du. There's my u. But what's e to the 3x? There's a leftover e to the 3x. What am I going to say e to the 3x is equal to? Well, I've got u equal to e to the 3x plus 1. So u minus 1 is equal to e to the 3x. So that right there, that's going to be u minus 1. That's the back substitution. Right? There's leftover things with x's in it after we deal with our u and our du. Then we have to use what we set u equal to figure out what to plug in for the leftover x's. So this ends up being the integral of u plus 1 divided by u times 1/3 du. Another way people do this, which I am less a fan of, but is still fine. Some people like to take this and completely solve for dx. They say, okay, dx is equal to du divided by e to the 3x. And then they go, I think I can fit this in here. They go, I'm going to write this as the integral of e to the 6x over e to the 3x plus 1 is u, and dx is du over e to the 3x. I think I lost a 3. Right, I did. I forgot the 3 e to the 3x. Sorry about that. But then e to the 6x divided by e to the 3x is e to the 3x because you subtract the powers. So you get the integral of e to the 3x times du over u, but then e to the 3x is u minus 1. So you get the integral of u, u minus 1, which is what I should have here. I wrote a plus for some reason because I'm just making mistakes apparently. U minus 1 over u du. And I forgot the 3 again. Gosh. Ugh. Sorry. The point is, it's the same either way. To me, this feels more normal, but I know that I saw some solutions that one of your professors wrote to a quiz, and they did it more like this. Either way is okay. They both work. I just think this feels more natural. In either event, to integrate this, we need to erase. Yeah. And say, okay, if I've got u minus 1 over u, that's equal to the integral of 1 minus 1 over u, just dividing each part by u. And then you get 1/3, the integral of 1 is u. The integral of 1 over u is the natural log of the absolute value of u plus c. And then we get 1/3 times u, which is e to the 3x plus 1 minus the natural log of the absolute value of e to the 3x plus 1 plus c. Whew. Okay, so that's an example of a back substitution where you've got leftover x's that you have to substitute in for. Let's do one or two more examples. Often they seem to come up when you've got square roots. So let's look at something like this. Let's look at the integral of 1 over 1 plus the square root of x. Doesn't seem like there's really any obvious choice. I'm going to go with the denominator again. I'm going to let u equal 1 plus the square root of x. The derivative of the square root of x is 1/2 x to the negative 1/2, and then times dx, which is the same as 1/2 root x dx. And yeah, I don't really know what to do with that here. So there's actually one way I could do it is I could solve for dx, and I could say, okay, dx equals 2 root x du. I know I just said this is not my preferred way of doing it, but it still works. I can plug that in here and then say, okay, this is equal to, well, again, that's going to be u. And I'm going to have the integral of 1, I just wrote the integral symbol twice. Be 1/u, and then dx is going to be 2 root x du. Right, that's my dx. But then look, the square root of x we can solve for. If we isolate the square root of x, we can say u minus 1 equals the square root of x. So we can actually rewrite this as the integral of 1/u. I keep saying a thing and writing the wrong thing. Sorry. 1/u times 2 root x. Let's bring the 2 out in front. And the square root of x is u minus 1. Well, this is actually the same integral we got to before. Right, this is, again, the integral of u minus 1/u. If we distribute the 1/u, we get 1/u times u minus 1/u times 1. And then we integrate. We get the same thing. We get 2 times u minus the natural log of the absolute value of u, c, and then plugging back in what our u was equal to, which is 1 plus root x, we get 2 times 1 plus the square root of x minus the natural log of the absolute value of 1 plus the square root of x. So these are both examples of back substitutions, where you had some leftover x's that you had to then use what you set u equal to figure out what to plug in for the leftover x's. We'll see a couple more examples of this as we go through class today, because I have a couple more examples that kind of pop up in other places. But let's go ahead and at least one other example. Yeah, I feel like I had a second one too. Let's go, let's see. Let me hit one other thing here. Someone had this question about their previous midterm from, I don't remember whose class. Doesn't really matter whose class it was. And then we'll talk about some area and volume. And then we'll talk about the midpoint rule. And then we'll talk about enrichment parts. Okay, so someone had this question. There's this question 2 from midterm 1 from, again, I don't know whose class. So assume you deposit $500 in an account whose annual interest rate is 3%, which is 0.03 as a decimal. And it's compounded continuously. Okay. Find the function that expresses the balance after X years and draw the graph of the function in the XY plane. So normally, if we know a principal and an interest rate and it's compounded continuously, we know that the formula for the amount of money you have after T years is PE to the RT, which is 500 times E to the 0.03 times T. However, they're asking us to use Y and X instead of A and T. So I would write this as Y equals 500 E to the 0.03X. So that's our function. And that just really comes from knowing, right, from having done it before, right? We've seen the continuously compounded interest formula a few times. We're kind of expected just to know it. So that's the function. And then if we want to draw the graph of the function, let's see here. So I've got an exponential function. And since my power is positive, I know it's going to be bigger from left to right. It looks like your usual kind of exponential shape, which is kind of just like this. And we want to find the y-intercept. If I set x equal to 0, y is going to be, let's see, 500 times e to the 0 is 500. So my y-intercept would be like 0, 500, and it would look something like this. And that's kind of it. Yeah, I don't know if there's a whole lot more to say about that problem. The second question, which I wasn't asked to cover, was how long until the balance triples. And to find that, we're just going to set y equal to 1500 and solve for x. That's how you figure out how long it takes to triple. Yeah. Certainly not a terrible question. Definitely got to think about it a little bit. Side. So I know you guys have I know the Lee students have a homework assignment due today on area and volume. Let's do a couple area and volume questions. I know people had a few different ones they wanted me to look at specifically. Yeah. So let's look at this area one, and then we'll do a few volume ones. We do need to move forward because there's new material coming your way. So here's an area question that a few people will have asked in office hours, and I don't know exactly the numbers, but let's look at this one. So we want to find the area of the region bounded by, try not to write, so I'm writing, these lovely functions, y equals 4 e to the x, y equals 4 minus x squared, y equals 2x plus 1, and x equals 4. So the issue here, one of the issues here is just knowing where everything intersects. And this is where you actually have to you have to have some graphing knowledge. So you could totally graph this all on Desmos and see where things intersect. That's one valid way of doing it. But let's go ahead and see what these graphs look like. So I know that 4 e to the x, just like 500 e to the 0.3x or 0.03x, if I set x equal to 0, I'm going to get y equal to 4. So 0, 4 is going to be an intercept. And the fact it's going to be an intercept for this graph as well, right? It's actually going to be the vertex of this graph. So I'm going to draw this graph first. So this graph's going to do this. And it's going to intersect at -2, 0, and 2, 0. And then 4 e to the x is going to do, let's use different colors if we can here. I have a fair number of colors I can use. I haven't exhausted all the colors. I have a new black pen I haven't used. Oh, I'm so excited. I'm running out of good black pen, so it's very exciting. I know it's like I'm super excited about that pen. It's very exciting to have a nice new black pen. Although this one I've just been using actually looks pretty good too. Banner day, new black pen. All right. So anyway, 4 e to the x is going to go through here, and it's not just going to be like above this function, right? It's going to come like that. So there's 4. Actually, we should extend it further to the right because we know we're going to have x equals 4 as well. So I'm trying to not make this look super kind of huge. Sorry, my graph might not be excellent. X equals 4 is a vertical line. Now I've lost my pen. So right, x equals 4 is something over here. So it's be a straight vertical line. And y equals 2x plus 1. So that's a straight line. It's increasing from left to right. It has a y-intercept of 1. It's probably going to intersect here somewhere. I don't know exactly where. But it's going to look like, probably something like that. So it looks like we're looking at this region here. And notably, as you go from left to right, it looks like this point here is kind of a breaking point where this region over here and this region over here have different top and bottom functions. So it looks like we need to find this point of intersection because we know that these intersect at the point 0, 4. And we know there's something on the floor here. Sorry, one sec. Oh, there's like a little bird in my sock. Interesting. Okay. And then we know that these ones over here intersect at 4, whatever. 9, I guess, and 4 comma 4 times e to the 4th, which is really large. But we need to find that point there. So we need to set this and this equal to each other. So if I set 4 minus x squared equal to 2x plus 1, let's solve. Oh, wow, this is a, I feel like I might have written something. This looks unfortunate, I think, unless I'm not, I'm wrong. I was missing it. Okay, this is not unfortunate. So I've got x squared plus 2x minus 3 equal to 0. You get x plus 3 times x minus 1. So we get intersection at -3 over here, which we don't care about, and +1 over here. That point there is the point 1 comma 3. Okay. So here's how we're going to set up the integral for the area. From here to here, right, the top function is 4e to the x. The bottom function is this parabola, which is 4 minus x squared. From 0 to 1. And then from here to here, right, we're going from 1 to 4. And the top of our rectangle is still 4e to the x. The bottom of the rectangle is now y equals 2x plus 1. And that's how you would set that problem up. I don't think we should spend our time evaluating that. I think you are all capable of integrating this and plugging in those limits of integration. Right, the integral of 4e to the x is just 4e to the x. The integral of 4 is 4x. The integral of x squared is x cubed over 3. I think you guys got this one. But that's how you would set this problem. So and definitely the setup is the hard part here, right? So, like knowing which region is. So you really have to kind of graph this one. Like there isn't a way to do this without graphing it to know exactly what the region looks like. You just, right, you can't set them all equal to each other and find all the points of intersection. You could, but it's still not going to be super clear without graphing. So I'm going to state this again. When you have more than 2 functions that you're trying to find the area of the region bounded by them or volume of the region revolved, if you've got more than 2 things you really, really kind of have to graph it. There's very few exceptions to that kind of rule. So yeah, we graphed it. Let's look at another one. I've got 2 different volume questions on my mind. Well, there might have been a third one. Let me take a look here. Okay, if you guys, yeah, I definitely, to the question that was asked, I would certainly recommend practicing being able to graph them. They don't have to be exact, like clearly my graphs are not perfect, right? But they get at kind of the point of where things intersect, right? So I know what 4e to x looks like that. It has a y-intercept of 4. I know what my downward opening parabola is like. I know what my straight line is like. I know what my vertical line is like. And I have a good kind of sense of where things might intersect each other. So yes, I would say spending some amount of time being able to graph things is probably worth your effort. It's obviously not the only thing, but it is a thing. So let me go ahead and look back here for 1 sec. Sorry. Okay, yeah, that's what I wanted to do. All right. So let's look at this. We have a region bounded. Let's see. Above by y equals the square root of x. Below by, what have we got here? Y equal to x over 7. And on the right by, oh, is x over 7 going to be terrible? I don't think so. Let me be careful here. Well, that should be fine. Maybe I should pick a slightly different number. Let's pick, something that's nice to take the square root of. Sorry, I was trying to pick fun numbers and now I'm like, that'll be too big. Okay. Fine, I can just do that. So 9 and on the right by. Okay. So find the volume of the solid revolves about the y-axis. I should say. Find the volume of the solid formed by revolving this region about the y-axis. Okay, so let's draw it. This one you could, no, you still should draw it. So when I draw this, I automatically know that y equals x over 9 is going to be lower than the y equals square root of x. How do I know that? Well, I know they're both going to the origin. Like the square root of x starts at the origin, and it gets bigger faster than it moves to the right. Right? The square root of x kind of has that shape. Whereas x over 9 is a straight line, right? It's not going to, the only line that's above the square graph that is the straight line that starts at the origin is the line that's the vertical line. Right? Any other straight line, even if it's got a super steep slope, there's some little region between that line and the square root where the line is below the square root. It looks like this. And I might not even care about that point of intersection. I don't think I do actually care about it. But I do care about the vertical line. I suppose I should check what it is to see, right? Is my vertical line over here, right? So I could be thinking, right, vertical line is here, and I want all the region over here because I don't want it to be bounded on the right by the vertical line x equals 9. But the vertical line might be way over here. So it actually does kind of matter what this point is. So let's find out what that point is real quick. I said the square root of x equal to x over 9. I'm going to square both sides. Say that x equals x squared over 81. So 81x equals x squared. So x squared minus 81x equals 0. So x times x minus, oh my goodness, equals 0. So let's say 81 is where they intersect. So this point of intersection is x equal to 81. So clearly x equal to 9 is way left of that. I'm not going to draw it perfectly to scale. I'm just going to say x equal to 9 is right there. So here is my region. Which I don't really want to draw that much on. So, right, my region is right there. I'm drawing on it. And I'm revolving around the y-axis, which is unfortunate because around the y-axis, I'm going to have two different kind of right-hand boundaries. So we know for the disk or washer method, when you revolve around an axis, your rectangles in your region have to be perpendicular to that axis. So if I draw a horizontal rectangle, which is perpendicular to my vertical axis, well, there's two different places I could draw. I could draw one down here, but I could also draw one up here. And these rectangles have different right-hand bounding functions. Okay, so we're going to use the washer method. Why not the disk method? Because to use the disk method, the axis of rotation needs to be one of the boundaries of your region. And clearly, the axis of rotation is not one of the three boundaries of our region. Right? These are the three boundaries of our region. Okay, so washer method. Washer method says, and let's kind of draw the whole thing out. So if we look at this smaller washer first, right, which looks like this. There's my smaller washer. The volume of that washer is pi times the larger radius squared minus pi times the smaller radius squared times the thickness of that washer, which is a small change in y. Which means we're using dy. We know we're using dy if we have a horizontal rectangle or horizontal strip. Okay, so for this particular strip here, my outer radius, which is kind of this amount here, that's just how far it is to this straight line function. But I have to do it in terms of x as a function of y. So the function, which is y equal to x over 9, is going to become x equal to 9 times y. And this function, which is y equal to the square root of x, is going to become x equal to y squared. So in this little spot here, up until we get to this breakpoint here, the outer radius is is x equal to 9y. And the inner radius is going to be, well, that really small radius is going to be x equal to y squared. All times dy. So the volume of this region that stops right there revolved around the y-axis would be the integral of all of this. We usually factor out the pi of 9y squared minus y squared squared from however low y goes, which is 0, to however high this region goes, which is right there where x equals 9 intersects y equals x over 9. So if this is y equals x over 9 and x is equal to 9, then y is going to be 9 over 9. This is going to be the point 9, 1. So my region goes as low as y equals 0 to as high as y equals 1. Okay, then we have to do the other region. Right? We have this rectangle revolved around the y-axis, which is going to look like this washer. And that washer has a different outer radius. Right? That washer, which I'm running out of room to write, typical. This washer here, the volume of that washer, is still the same formula, right? It's still pi times the big radius squared minus pi times the little radius squared times dy. But now my outer radius is different, right? No matter where I draw this strip, the outer radius is x equals 9. The inner radius is still the y equals square root of x, or x equals y squared function. So the volume, the total volume of the shape would be this volume plus the volume of the green part revolved around, which would be pi times the integral of 9 squared minus y squared squared again. From as low as where it changes from red to green, which is as low as y equals 1, to as high as whatever this point is here. Well, if x is 9, this is the y equals the square root of x function. So if x is 9, y is going to be 3. So it's going to be from 1 to 3. That's how you would set up that problem. Again, I think our time is best spent setting up the problems. I am confident all of you could integrate this. I know the arithmetic gets a little bit messy here, but it's not terrible, right? I mean, fine, I'll do one more step. So if I were taking a test and I was limited on time, I would write this all as, I would simplify it a little bit. I would say that this was equal to the integral from 0 to 1, pi times integral from 0 to 1 of 81y squared minus y to the 4th plus pi times the integral from 1 to 3 of 81 minus y to the 4th. And then I would integrate. I'd get, let's see, 81y cubed over 3 is going to be 27y cubed minus y to the 5th over 5 from 0 to 1 plus, I'm factoring out the pi for everything, 81y minus y to the 5th over 5 from 1 to 3. And then I'd plug in the 1 and the 0 here and the 3 and the 1 here. So I would probably, I would maybe consider stopping there if I was really short on time, or if I wasn't, I would plug in what I would get. So I get pi times 27 minus 1/5, plugging in 0 to 0, plus 81 times 3 minus 3 to the 5th over 5 minus 81 minus 1/5. And I would definitely stop there, right? We don't want to evaluate that unless you've done all the other tests, you're super 100% confident, like I got everything else right and I've still got 5 minutes left. I'm going to go back and make that fraction look nicer. But otherwise, you should not. Okay. Let's do one more volume question. It's actually like 4 more volume questions, really, or 3. Let's do one more volume example. Okay, so let's see here. Set up intervals to find the volumes of the solids formed by revolving the region bounded by the graph of y equals, let's be nice. What do I want to pick here? Sure, let's do y equals something kind like 49 minus x squared. So sorry, it's the region bounded by y equals 49 minus x squared and y equals 0. And then we're going to have about the following lines. So we're bounded by this. We're going to do revolved around. I'm going to make a few extra choices here. Sure. So we'll do y, let's do y equals 0 first of all. Let's do y equals -3. Maybe we'll do y equals 52. And then we'll do x equals 8. Okay. So you don't have to draw the region here, but it's not that hard to draw, right? It's a downward opening parabola. I think it's worth our time to draw it. Something like this. Here's y equals 0. And these points of intersection are -7, 0, and 7, 0. So first and foremost, I want to go around y equals 0. So y equals 0 is one of our boundaries, which means we're going to use the disk method since our boundary is the axis of rotation. So for around y equals 0, right, here's our thing. We're rotating that around y equals 0. When we rotate that around this line, right, we're going to get a disk. And the volume of that disk is just pi r squared dx. Where the radius, and this is the important part, right? We're always saying the volume of a disk or the volume of a washer, right? Volume of a disk is pi r squared d whatever. Volume of a washer is pi times the big radius squared minus pi times the little radius squared times d whatever. And the radius is variable, right? If you draw your strip way over here, your radius is much smaller. If you draw your strip way here, it's as big as possible. So the radius depends on x, and the radius is exactly whatever the height of that function is. So here, our volume of our disk is pi times 49 minus x squared is our radius, quantity squared times dx. And then the volume total would be the integral from as far left as the vertical rectangles can go to as far right as they can go, which is from -7 to 7 of pi times 49 minus x squared dx. That's how you'd set up that integral. Okay, let's change it up a little bit. Let's go around y equals -3. That's a little bit over here. Yeah, I can use that too. So if we're going to go now around y equals -3, we can no longer use the disk method because our region is no longer flush with the axis of rotation. So what we're thinking about still is taking this strip and revolving it around this axis. Well, when you sweep this out around, right, this part, if you reflect it over, right, it's about like probably down there. And that part's like there. It's not. I'm blowing it. Sorry. Blowing it a little bit. Sorry, something my brain. Sometimes the pictures are like, okay, James, come on. Yeah. Okay, here we go. That's the problem. Don't need that input there. There we go. So there's our washer. And the volume of this washer is pi times the big radius squared minus pi times the little radius squared times dx, which is going to be, so now the big radius, it's still, we're still using this further away function, but now that further away function is, right, this length here to the axis of rotation compared to this length here, right, that got 3 longer. My outer radius here is 49 minus x squared minus 3. And my inner radius here is my inner function, which was 0 minus 3. All times dx. So to find the volume for this one revolved around y equals -3, the volume would be still the integral from -7 to 7. I'm going to factor out the pi, and I'm going to have 49 minus x squared minus 3. And I'm writing it that way to really kind of emphasize the fact that it's your function, or it's the distance to your function. So this distance, oh my gosh. It's the distance from your function to the axis of rotation. So it's the distance from y equals 49 minus x squared to y equals -3. And when you find the distance between two things, you subtract. Minus 0 minus -3 squared. Same deal here, right? The distance from y equals 0 to y equals -3 is always going to be 3, which is 0 minus -2. Okay. For y equals 52, which is up here, so now, right, if we take this strip and revolve it around that, we're going to get something that's, I'm sorry, I know I'm not over here. Right? It's going to go up like that. And so our outer radius now, so for y equals 52, our outer radius is 52 minus 0, right? The function that's further away from the axis of rotation uses your big radius. And y equals 0 is further away from y equals 52. And our inner radius is going to be that amount there, which is going to be 52 minus the function, 49 minus x squared. So the volume around this is going to be pi times the integral from -7 to 7 of your big radius squared minus your smaller radius squared. Okay, so all of those ones basically, they're all, right, it's always disk or washer method. And you're always just trying to think about what your outer radius is, so your outer radius is always the function that's further from the axis of rotation. So it depends on where the axis of rotation is, right? If the axis of rotation is up here, your function further away is down there. If your axis of rotation is down here, your function is further away is up there. Wouldn't that be so? So someone asked me a question. Wouldn't that be solving for the area on the outside of the parabola? And my answer is no. None of these are giving the area that is outside of the parabola. They're giving you different shapes. So, for example, I'm going to erase some stuff here. I can see what the other side, right? So, for example, the first one that was revolved around y equals 0, I'm going to draw some very kind of basic pictures here. Like the first one kind of would look kind of like an egg, right? Because you take that and you would revolve it around this way, and it's going to kind of duplicate over. And it's going to look, you know, like that. On the other hand, when you take that same region and revolve it around now this line down here, we're going to be missing some center part. So it's going to be kind of like this egg, but with a hollow, like someone like drilled a hole through the middle of it. So right, you've got this same sort of deal here. Sorry, I mean, pictures are not excellent. But hopefully you guys can kind of see that, right? It's kind of like an egg that someone drilled a hole through the side of. But then if you rotate around the other line that we had, which was above it, we take this region again and revolve it around something up here. We're going to be flipping it over that way. So it's going to look, you know, solid. So it kind of looks like on its side. So if you turn that on its side like this, it kind of looks like a cylinder, but you've kind of like hollowed out. Like it kind of looks like one of those, you've seen those things in the mall where you put your quarter or nickel in and it like goes around and around and around and around, and it goes like through the middle. I think they're kind of fun. I will always put a nickel in one because it's cool to see it go down the middle. But it kind of looks like one of those, except doubled, so that there's one kind of going the other side as well. It kind of looks like a tire. Yeah, but the problem is the tire usually doesn't have quite as much volume in here, right? The tire is more like this, and then you've only kind of got just like that, right? So right, this shape has a little bit more, right? It has some extra volume there. Anyway, so no to the question, we're still getting what's quote unquote inside the parabola, right? We are getting all of this area revolves around that way. Okay, there was one more part to this question. It's kind of a fun drawing. I mean, I'm not saying you're wrong, Madison. I do think it looks tire-esque, just not exactly like what we think a tire looks like. Yeah. Maybe a tire with some really kind of super wacky rims. Okay, there was one more question which was going around x equals 8. So around x equals 8, things are a bit different because the orientation of our axis of rotation has changed. If we're looking at this region revolved around, and I'm going to draw this so that I can, well, I'll start this way. So here's x equals 8. So now that we're going around the vertical axis, we have to have a horizontal strip. So when I revolve that strip around, I'm going to get a washer. All right, when I do it there, revolve this thing. Do right, that kind of deal. And the volume of my washer, just like every other time, is pi times the big radius squared minus pi times the little radius squared times d something. In this case, it's got to be dy, because that is a small change in y, whereas a vertical rectangle is a small change in x. Okay, so sorry, words here. We have to take this function and solve it for x as a function of y. So that was y equals 49 minus x squared. So then x squared equals 49 minus y, and x equals plus or minus the square root of 49 minus y. This right side, that's x equal to the positive square root of 49 minus y. This left side, that's x equal to minus square root of 49 minus y. So then my outer radius is this minus this. So my outer radius here is 8 minus the negative square root of 49 minus y. And my inner radius, right, the function that's closer, or the distance between the axis and the function that's closer, is going to be 8 minus the positive square root of 49 minus y. So then to find the volume of this thing revolved around, and the shape looks kind of like, right, if you take this parabola, make it a little smaller, and you revolve it around this line here, it kind of looks like, I don't think it really looks like anything in particular. It kind of looks like a bundt cake, I suppose, right? Like one of those cakes where you're missing the middle. I totally somewhere have a cake mold that looks exactly like this, but I can't seem to find it anywhere. So anyway, that's what this looks like. And the volume would be the integral of pi times your big radius squared. So 8 plus the square root of 49 minus y squared minus your little radius squared dy from as low as y equals 0 to as high as y equals 49. Fun times. So when you're revolving around a different axis of rotation other than the y-axis or the x-axis, your radius is always going to be the difference between your function and your axis of rotation. And sometimes it's the axis minus the function, if your axis is the bigger thing. Sometimes it's your function minus the axis. So I'm not going to do it. But if we were revolving around the line, say like y equal to -10, then the bigger radius would be this function minus -10. And the smaller radius would be this function that's closer minus -10. Always the difference between things, and it's always the bigger one minus the smaller one. So in this case, the axis of rotation has the bigger x value, right? It's further to the right. In this case, the axis of rotation has the smaller x value, it's further to the left. Same deal for y's, right? When the axis of rotation was below the region, smaller y value, we did our things minus the axis of rotation. When our axis of rotation was above, meaning it had a bigger y value, we did the axis of rotation minus the things we had. Okay. So let's take a few minutes, not a lot. And so usually in the syllabus, the midpoint rule, I know it's like in this section of the book, like it's section 5.6 or something. But usually it gets kind of pushed to the end of the class. Was the upper limit of the last one was 49, because this point of intersection here was, or this intercept was 0, 49. Right? The lowest y value was as low as y equals 0, and the highest y value was as high as y equals 49. So when you're using a horizontal strip like that, your limits of integration are always how low y is and how high y is. When you're using vertical rectangles, your limits of integration are always how far left x can go and how far right x can go. Okay. So the midpoint rule is for approximating. Area under a curve. why would we do this if we have the fundamental theorem of calculus that allows us to just find the area under the curve? Well, there are some functions that cannot be anti-differentiated. You cannot use the fundamental theorem of calculus for them. So let's go ahead and grab, yeah. So let's look at this example. So I'm going to do an example that's actually similar to the homework. So let's say we have this function. So I'm going to say f of x equals, sure, we'll do this one, 3x over x plus 1 on the interval from, I'm going to change this up a little bit to make it slightly less terrible. Let's do the integral from 1 to 4 with n equals 6 subintervals. Okay, so let's draw this thing. Sure. So 1, 2, 3. Let's see, and let's plug in this. So plug in 1, I get 0, 2, sure. Plug in 2, I get 6, which is, that's even bigger. Okay, interesting. Cool. When I plug in 2, I get 6 over 3, which is 2. And I plug in 3, I get 9 over 4, which is a little bit bigger. Awesome. Plug in 4, I get 12 over 5, which is a little bit cool. So here's what this function looks like. When I plug in 0, I get 0. And there's a vertical asymptote over here. Don't really care about that though. Okay, so I'm trying to approximate this area. I'm going to use n equals 6 subintervals. So I'm going to take this interval from 1 to 4 and divide that length into 6 equal subsections. So 4 minus 1 divided by 6 is 0, 6, which is 1/2. So each of those subsections, so this is 1.5, this is 2, this is 2.5, this is 3, this is 3.5. And then what we're going to do is we're going to say, I'm going to, for each of these subintervals, I'm going to then find the midpoint of that subinterval. So the problem that he's given you on your homework with 10 subintervals is kind of a giant pain in the butt. I'm not going to lie. Because for each interval, you then have to say, okay, what's the midpoint there, and there, and there, and there, and there, and there. Whatever that midpoint is, we're going to use that point to find the higher rectangle. Now, the nice thing about the midpoint method is it does give you a pretty good estimate. So here's how we're going to calculate the area of these rectangles. So usually we call this calculation M6. M for midpoint, 6 for the number of subintervals we're using. And that's going to be just all the areas of the rectangle. So it's going to be the area of the first rectangle. So it's going to be the base times the height plus the base times the height plus the base, right? So it's going to be, let's see here. Each of these bases are the same. Each rectangle has a base, a rectangle base of 1/2. Awesome. Now we have to find all the heights. So the height is going to be the function value evaluated at 1.25. So it's going to be f of 1.25 plus the next one's going to be f of 1.75. The next one's going to be f of 2.25. The next one's going to be f of 2.75. The next one's going to be f of 3.25. And the last one's going to be f of 3.75. But then you have to take all this and plug them into that function and then probably use a calculator. So, right, so doing this, it's really kind of gross. We're going to get, and I'm not going to calculate this because it's a pain, but we're going to get 1/2 times Let's see, I'm gonna plug, so we get 3 times 1.25 divided by 1.25 plus 1. And then I'm gonna get, right, 3 times 1.75 divided by 1.75 plus 1. And it just goes on, right? 3 times 2.25 divided by 2.25 plus 1 plus 3 times 2.75 divided by 2.75 plus 1. 3 times 3.25 divided by 3.25 plus 1. And finally, 3 times 3.75 divided by 3.75 plus 1. And that would give you an approximation of how much area is under this curve. Now, this particular function is integrable. You can anti-differentiate this, plug in your limits of integration. But there are lots of functions, probably the most famous of which is e to the x squared. E to the x squared is not anti-differentiable. You cannot find an antiderivative for it. So if you wanted to find the area under the curve from 0 to 1 of e to the x, under the curve e to the x squared from 0 to 1, you would have to use some approximating method like this. We can, however, find the area under this curve. So I don't know what this is. It's some gross number, right? We could, I mean, you could do some you could factor out a 3, but it's just kind of, it's gnarly. This is what, 5/4 over 5/9, 5. Yeah, I shouldn't get started on this stuff. So, yeah. I do want to show you though how you could, and so I'm not just like doing this for no reason. The homework problem from Ma does also ask you to actually straight up integrate it. So let's talk about that part. So what if I want to do the integral from 1 to 4 of, what did I have, 3x over x plus 1? Yeah. So do you substitution. But you can't break this up into 2 fractions because you got a denominator that has more than one piece. So u equal x plus 1. And our du is just going to be dx. Okay, so when I start replacing things, look what happens. I get a u, my dx becomes du, but I've got an x left over. What do I do? What did we do at the beginning of class today? We did a back substitution. So this x here, well, I can say that u minus 1 is equal to x. So this is going to be 3 times u minus 1. That's your x right there. And I would also change our limits of integration. So if x equals 1, u is going to be 1 plus 1, which is 2. And if x equals 4, u is going to be 1 plus 4, which is 5. So now we can factor out the 3. U divided by u is 1. 1 divided, it seems like this one comes up a lot with the back substitution. 1 divided by u is 1 divided by u. When we integrate this, we get 3 u minus the natural log of the absolute value of u from 2 to 5. I'm not going to plug back in that u is equal to x plus 1 because I already changed my limits of integration. So I'm just going to plug in, right, this is u equals 5 and this is u equals 2. So I'm going to plug in 5 and I'm going to get 5 minus the natural log of 5. And then I'm going to plug in 2 and I'm going to get 2 minus the natural log of 2. And then you can simplify this a bit. 5 minus 2 is 3. This is plus natural log of 2 minus natural log of 5. Some people would simplify that as natural log of 2/5. This is 3 times 3 plus the natural log of 2/5. Okay. And then if you calculate the thing on the other side of the board, you would be able to see that this number here and that number there are not too far from each other. Yeah. Let's do one more. This one's actually going to segue into talking about integration by parts. So let's say, let me be smart on my choice here. I'm going to be smart on my choice or not. No, I don't do that smart. Oh, well, that's fine. So let's say I want to approximate the area. I want to approximate this integral. Let's just write it that way. I want to approximate the integral from, I don't know, 1 to, let's not make it too terribly, from 1 to 3 of natural log of x to the 4th power dx, using n equals 4 subintervals with midpoints. I'm sorry, and that should be not natural log of x to the 4th like that. I meant to do, sorry, natural log of x to the 4th. And so before I did anything, I would probably actually rewrite this. I would probably rewrite this as 4 times the integral from 1 to 3 of natural log of x. Right? Because you can definitely take that 4 down in front. Okay. So we're going to do the same sort of thing. Natural log of x looks kind of like this. Go from 1 to 3. I'm going to break that up into 4 equal subsections. So that's 1.5, that's 2.5. So then if I want to estimate the area of those rectangles using midpoints, right? The midpoints are half. So I always like to kind of be like, here's my interval from 1 to 3, break it up into 4 sections. Bless you.
Thank you.
So there's my 4 sections. Right. And then we need the midpoint of each of those sections. So the midpoint of that section is 1.25. I happen to pick numbers that were similar to the previous time. Sorry. The midpoint there is 1.75. The midpoint there is 2.25. The midpoint there is 2.75. So then to estimate the area is going to be the base of each of those rectangles, which again is 1/2. Sorry for not changing it up. I should have made it different. The height of each of those rectangles is going to be, well, the height of the midpoint. So it's going to be the natural log of 1.25 plus the natural log of 1.75 plus the natural log of 2.25 plus the natural log of 2.75. Which I suppose you could simplify, but it's not going to be very nice. It's 1/2 the natural log of this times this times this times this. Technically, write it that way if you really wanted to. So that's very briefly the idea of the midpoint rule. Yeah, you take your interval, divide it into the number of subintervals that you're supposed to be using. That's going to be usually told to you. And then for each of those subintervals, find the midpoint of that subinterval, use that to find the height of your function, multiply it by the base of your rectangle to find the area of the rectangle. Okay, how much time? We got 13 minutes, yeah. So let's start talking about integration by parts. And I feel like I should just do a couple of examples, and then on Thursday we'll get more into the nuts and bolts of how it works, or really more why it works. So for integration by parts, the idea is typically that it's really kind of actually undoing the product rule. So for example, if I wanted to, I really feel like I feel like I owe you guys a small explanation of how it works, even though. So here's a very, very quick explanation. We'll do it again on Thursday. So we know the product rule. We know that f times g prime is equal to f prime g plus f g prime. And so similarly, I'm going to write that uv prime is equal to, I'm going to write u prime as du. And I'm going to write v prime as dv. Okay, then I'm going to iterate both sides. Okay, but then we're going to rewrite this as, well, the integral of the derivative is just the function. And write this as the integral of v du plus the integral of u dv. And then we're going to subtract this over here. So the integral of u dv is equal to uv minus the integral of v du. So here's the whole idea. We're going to be starting with something like this. We're going to pick what u and dv are, and then we're going to rewrite it like this in the hope that it gets easier to deal with. Let me show you an example. And sorry, I don't think I'm going to get, I was going to try and get to the natural log of x to the fourth integral, but I don't think I'm going to have quite enough time. So I'll save that one for Thursday. Let's say I want to integrate, I don't know, let's say 3x times cosine of x, which we don't know how to do. In fact, let's call it 2x. I really want to stress that this is not equal to x squared times sine of x. Because of the product rule. The derivative of that would be a product rule derivative. It would be 2x times sine plus x squared times cosine. It's not that. So instead what we're going to do is we're going to say, well, I'm going to let u equal 2x. I'm going to let dv be the rest, which is cosine of x dx. So whenever you're picking u and dv, once you pick u, dv has to be everything else that's left over. Yeah. So then we find du and v. So du, the derivative of 2x is just 2 times dx. And v is the antiderivative of dv. So v is going to be sine of x. All right. So now here's what I'm going to do. I'm going to say that my integral of u dv that's going to equal, because of the formula that we just talked about, it's going to equal u times v minus the integral of v du. Okay, so u is 2x, v is sine of x, and v is sine of x, and du is 2 dx. I'm going to put the 2 out in front. No, I'll put it here. Well, look, this got easier. We know how to integrate sine of x. It's just negative cosine of x. So this is going to equal 2x times sine of x minus the integral of sine is negative cosine, so it's negative cosine of x times 2 plus c. Or as most people would probably write it, 2x sine of x plus 2 cosine of x plus c. So that's what we did. We took an integral that was complicated. We made a choice for u and for dv, and then rewrote the integral in terms of being u times v minus the integral of v du. And this new integral of v du was easier to manage. That's the whole plan of attack with integration by parts, is you're trying to make a choice for u and for dv so that the integral of v du gets easier. Typically, we only use integration by parts after we've thought about using u substitution. So here's two different problems. Integral of x e to the x squared dx versus the integral of x, x e to the x dx. One of these is an integration by parts problem. One of these is a U substitution problem. Which is which? Well, I'm going to try U sub for both. So I'm going to do a U sub here. Yes, I can. I can let U equal x squared. Du is going to be 2x dx. 1/2 du equals x dx. So the x dx becomes 1/2 du. And this is 1/2 the integral du. And then I've got e to the u, which is going to be 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. That's a c, by the way. Okay. On the other hand, this one I could not do a u sub for. I could try, it's not going to work out. You can let u equal x, that's never the right choice if you're doing a u sub, because you just change all the x's to u's and it's still the same question. U equal to x is a perfectly fine choice when you're, I guess we pick 2x here, but if this had been x times cosine of x, picking u equal to x would have been perfectly fine for integration by parts. Yeah, there's, I mean, if I pick u equal e to the x, my du is e to the x dx. So then I'm integrating, let's see, du and x. If I take the natural log of both sides, I get natural log of u. But here's the problem. Integral of natural log of u requires integration by parts. So we haven't made our lives any easier. So this is definitely integration by parts. And so typically we are going to use integration by parts or U substitution if we have what I call a mixture of things. Right? We have a mixture of, like, this is x to a power, this is an exponential. This is x to a power times an exponential. So you have a mixture of things that's usually going to be a U sub or integration by parts problem. So let's try integration by parts here. And there's kind of a methodology for what you're going to pick for U and for dv. We often pick, there's a number of ways people talk about what to pick for U. You want to pick U to be the thing that will get simpler when you differentiate. Another way people talk about this is dv should be the most complicated thing on the board that's still easy to integrate. So most complicated, but still easy to anti-differentiate. So with both of those things in mind, it seems like U should definitely equal x and dv should definitely equal e to the x dx. Right? The derivative of u gets simpler, right? 1 is simpler than x. And the antiderivative of e to the x is very much easy to do. It's also worth pointing out that if I pick u equal e to the x, its derivative is e to the x, it doesn't really get simpler. So we almost never pick u equal to e to the x. And so then this integral is going to be equal to u times v, which is x times e to the x, minus the integral of v du, which is e to the x dx. And then the integral of e to the x is just e to the x. So we end up getting x e to the x minus e to the x plus c. Great. Sure, let me throw that. So let me go ahead and I think I got time to squeeze the natural log of x1 in here. But so here's kind of this is not a hard and fast rule, but it works most of the time. It's called late. This is how you pick u. First, you look for a logarithm. If there's no logarithm, then you look for an algebraic thing. When we say algebraic, we really just mean x to a power. Then if there isn't that, you pick u to be a trig thing. And then if you've gotten over to this, it's probably not integration by parts. So bear with me, I'm going to do two quick problems here. I want to integrate, say, x squared times natural log of x dx. I'm going to pick u equal always to the natural log of that one. So u is the natural log of x. And then dv has to be everything else that's multiplied by natural log of x. So dv has to be all of x squared times dx. du is 1 over x dx, like the derivative of natural log of x. V is the antiderivative of x squared, which is x cubed over 3. So then throwing this all into the formula. Oh, by the way, there's a thing we call this formula. It's ultraviolet super voodoo. uv minus the integral of v du is the ultraviolet super voodoo. Hopefully you remember that. So in this case, we're going to get u, which is natural log of x, times v, which is x cubed over 3, minus the integral of v, which is x cubed over 3, times du, which is 1 over x dx. Did our integral get simpler? Yes, it did, because we can simplify that. Right? That's going to simplify as x cubed divided by x is just x squared, and the 1/3 I'm going to put out in front. That's way easier to anti-differentiate. Right? I know how to do that. That's going to be, still have this front part here. Antiderivative of x squared is x cubed over 3. Cool. All right, it's not 10:20 yet, so I don't feel bad about starting another problem. It's not true, I feel a tiny bit bad, but not that bad. If you guys want to see this, and it's quick. So you might be wondering, how do you integrate something like natural log of x or natural log of x to the 4th? Well, for natural log of x to the 4th, you bring the power down, right? Because it is a natural log of quantity x to the 4th, which is equal to 4 times natural log of x. Yes. So, and I'm going to bring the 4 out in front and front. So for one like this, we are going to use integration by parts. We're going to pick u equal to the natural log of x. And let me ask you guys, if I pick u equal to the natural log of x, what's left in the integral to set dv equal to? Well, there's only one thing left in the integral. Or if you prefer, you can say it's 1 times dx. So then the derivative of u, the derivative of natural log of x is 1 over x times dx. And then the antiderivative of 1 is x. So then this becomes 4 times your ultraviolet super voodoo. U times v, so x times natural log of x minus the integral of v du, x times 1 over x dx. Be careful. When you get to this stage here, you always want to simplify this integral as much as possible before you do anything else. So this is going to be 4 times x natural log of x minus the integral of x times 1 over x is just 1. So that ends up being 4 times x times natural log of x minus the integral of 1 is just x. And that's how you integrate natural log of x. So specifically, I would encourage you all to probably remember, although you want to be able to show it as well, that this part here, that is the antiderivative of the natural log of x. There is no absolute value in here. It's just x natural log of x minus x.